Hi, Miss Barber here. I sure hope you're doing well. In this example, we're going to look at two graphs and determine if they are equal, isomorphic, neither, or both. Consider the graphs represented by graph 1. The set V consists of the elements A, B, C, D. The letter V is to suggest vertices, and the set E, which consists of the sets AB, AC, AD, and CD, the letter E to suggest edges. So graph 1 has 4 vertices, 4 edges, and the vertex starting at A is a degree 3. Now graph 2 is represented by this drawing. It's 4 segments with vertices A, B, C, and D. A and B are connected, that's an edge, so are AC, BC, and CD. The first question posed is, are graphs 1 and 2 equal? And the answer is no. They are not equal. Now, I didn't know this right away. I had to look at it for a little bit. I know that they are not equal because we notice that there is an edge in graph 1 from A to D. So in graph 1, okay, we have an edge. AD is an element of the edge, but in graph 2, no such edge. That is, and let's go ahead and write it, no edge connecting A and D. So we know they're not equal. The second question is, are they isomorphic? And that's a trickily worded question. A better way to word this is, can you build an isomorphism between graphs 1 and 2? You do a quick study of isomorphism's roots, and it means a bijective morphism. So the first thing we need to ask is it bijective? And the answer is yes. You can build a function from graph 1 to graph 2 in which it is 1 to 1 and onto. So for question number 2, okay, we start out with it is bijective, so that's a good start. Now the next thing is, and what I like to do is just make a chart. So I'm going to have a chart for graph 1 and a chart for graph 2. And I list the vertices. So the vertices that I see for graph 1, okay, it's in the set is A, B, C, and D. And graph 2 are the dots, right? And so we can write those A, B, C, D. Now, the key happens with the edges, the numbers of them, and the degrees of the vertices. So on the edges, okay, what we're going to do is see if we can make a one-to-one mapping. We notice that we have AB as an edge for graph 1. We have AC as an edge for graph 1. And we also have CD as an edge for graph 1. Let's see if I can do a similar thing for graph 2. Yeah, I know I forgot one. I'll come back to it in a minute. Okay, from the graph 2, I see that, I do have an AB. And what else do I have that I want? I have an AC, and I even have a CD. Okay, the issue happens when I look at this and realize that I have an edge AD in graph 1 that I don't have in graph 2, but in graph 2 I have BC. And so we could rename the vertices to make them be a better fit. And the one thing that's left to do is count the degrees of the edges. So if we go to the first graph, I have A. So the degree of A, here I'm running out of space. The degree at A is 3. Let's look at the next one. The degree at B, none. Oh, well, 1 by itself. I'm sorry, that was silly of me. And then we look at the degree at C, and I notice I've got 2 of them. Right, please. And the degree at D, and it happens twice, so that's also. So I've got a 3, 1, 2, 2. Now let's look at my drawings here. So I want to look at the degrees of each of those vertices. So degree at A is 2. That doesn't match, but maybe there's one we could match it to. Degree at B, how many edges are coming out of the vertex? That's 2. Degree at 3 is 3. We've got 3 edges coming out. And degree at D is just 1. So look at this. We have bijective behavior between the vertices. We have edges that do the same thing and the degrees that correspond. So in fact, these two graphs are isomorphic.